In the previous video, we defined the set GL2 to be the set of 2 by 2 matrices where the determinant of the matrix was not equal to 0. It's important to remember that we also reviewed that the determinant of the matrix is, for a 2 by 2 matrix, just the product of the main diagonal minus the product of the off diagonal. It's worth noting that determinants of larger matrices are harder to find. And we also defined a multiplication on the set of 2 by 2 matrices that looked like this. So there are our two 2 by 2 matrices, and the product matrix is AE plus BG, AF plus BH, CE plus DG, CF plus CH. And this is the standard matrix multiplication definition. And it comes from doing things that are dotted. And we went through that carefully in the previous video. We also showed that, well, I made the claim that GL2, under its matrix multiplication, is a group in the last video. And in the last video, we did show, so we showed that GL2, under its multiplication, is closed. That was the previous video. In this video, we will show, so we will now show that GL2, under its times, is associative. And that is, of course, the second of the 4 group axioms. So let's look at what that means. We're going to need to have A, B, and C all be elements of GL2. And we need to show that if I look at A times B times C, and I put parentheses around the A and B, that's going to be equal to A times B times C, where the parentheses around the BC. Now, to do this particular kind of a calculation requires some fairly tedious algebra skills, but nothing overly hard. I do want to set up the notation that we're going to need. We're going to need to let A be the matrix A, B, C, D. We will let B be the matrix E, F, G, H, and we will let C be the matrix I, J, K, L, where all of these little letters are simply real numbers. Now, all it is we need to start with one side and do the calculations and keep manipulating things until we can see that the other side is also equal to what we started with. So let's get started. I have the calculations already done, so feel free to listen to what I'm saying about the algebra and then rewatch the video if you want to take the chance to stop the video after each step to copy down what I've written very carefully. So here's A times B in parentheses times C. And this is just putting in our 3 matrices. When we do this first matrix multiplication, this is what we get. And you can stop the video and verify it if you want to. But what I want to do is I want to think about what we need to do the next multiply. For the next multiply, I'm going to be dotting this particular row with this column, then this particular row with this column. And the second row gets dotted with the first column, and the second row gets dotted with the second column. And when we do that, this is what pops out. Now, you'll notice that I have kept things fairly nice and straight so that you can see that this entry really is this row dotted with this particular column. And likewise, this particular entry is the first row dotted with the second column of the second matrix. And here, this entry is the second row of the first matrix dotted with the first column of the second matrix. And finally, this 2, 2 entry is the second row of the first matrix dotted with the second column of the second matrix. Pardon me. The next step in algebra is to actually do all of these little multiplications out. And when we do that, this is what we get. Now, at this stage, what we're trying to do is rewrite this product as a matrix product where we have the A matrix isolated by itself. And so, what that basically means is that I want to focus in on this A and this B and this A and this B and this C and this D and this C and this D. Likewise, the AB over here and the CDs over here. And the reason that I want to do that is I want to remember that A is the matrix A, B, C, D. So I want to try and get those separated out in a place where I can think about this as a matrix multiply of this matrix times something else. So the first thing that I'm going to do is I will reorder each of these 4 entries where I'm collecting the A's first and then the B's, and I'm collecting the C's first and then the D's. And when I do that, I get this particular matrix. And I've highlighted the A's and B's in white. And at this point, I can now factor out an A from those 2 terms and a B from these 2 terms. Likewise, I can factor out a C from those 2 terms and a D. I can factor out an A and a B. I can factor a C and a D. And when I do that factoring, we wind up getting this particular matrix. And I want you to stare at this matrix for just a minute. You'll notice that we have the A and the B, we have the C and the D. Likewise, the A and the B and the C and the D. And it's important to understand that this chunk and this chunk are the same thing. This chunk and this chunk are the same thing. And this chunk and this chunk are the same thing. No, not quite the same thing. This chunk and this chunk are the same thing. And this chunk and this chunk are the same thing. And because of those patterns, what this says is that the matrix that we are looking at can be rewritten as the matrix A times this matrix here. Because if I go backwards from this step to there, and I think about dotting that row with this column, that entry is what I'm going to get. And when I dot this row with this column, I pick up this entry up here. And when I dot this row here, the second row with the first column, I pick up the first entry in the second row of that particular matrix. And when I dot the second row of the A matrix with this column, I pick up the 2, 2 entry of that matrix up there in that previous step. And I am noticing that I've got a missing parenthesis, so let me put that parenthesis back. Now, it's important to understand that all we have to do at this point is look at this matrix and realize that it too is a product matrix. And we can kind of see that if I do some highlighting and look at the fact that we've got an EF there and an EF there, a GH here and a GH there. And we also have an IK here and an IK there, a JL here and a JL here. So when we put this together, we can realize that the matrix that we're actually looking at for this particular matrix here is nothing more than EFGH times IJKL. In other words, if we multiply these two matrices together, this matrix right here is what we get. And of course, the final step is to realize that this is matrix A, that's matrix B, and that's matrix C. And hence, we have indeed shown that AB times C is equal to A times parentheses BC. And what this means is that GL2 under its times is associative. In the next video, we will finish the proof that GL2 is a group by looking at the right identity and right inverse axioms.